And this is joint work with my students Matthew and Seth, and with our excellent postdoc Jiming. So we've heard a lot about different models of interactivity and local privacy at this workshop. Let me give you a quick sort of pictorial representation of what they mean before saying a little more formally. So you've got your devices, and this is similar to the slide that Abradeep had this morning, except he apparently had a better idea than me about what the cloud looks like. But sort of informally, if you're non-interactive, what that means is that all of the communication can be fully parallelized. Okay, so everyone's device looks at their own data, runs some local randomizer, and simultaneously can send all of the information to the server. Okay? On the other hand, we could ask for a more general model, the sequentially interactive model that was defined in Ducci, Jordan, and Wainwright. And informally, it looks like this. Now, information is sent sequentially to the server, and the message that the ith person sends, right, the randomizer that he runs, can depend on the previous messages that were sent, on the previous outcomes. But what you cannot do is go back to someone who was previously queried and ask them another question. Okay, so in particular, only n messages are sent. And then finally, you can have the fully interactive model in which there are essentially no constraints. So people can send messages in any order. There's no limit to the length of the protocol. In particular, each person might end up sending many, many, many messages. Okay. Okay, so I was going to leave it at this, but something I didn't realize before attending this workshop is, as a community, we apparently don't agree on what the definition is of privacy in the local model. So let me tell you what I mean by it, and it's somewhat, I mean something somewhat more general and more permissive than some of the other talks we've heard so far. Okay. So first of all, because the main thing that I want to talk about in this work is sample complexity, to make that make sense, I'm going to assume that there's an unknown distribution D from which all of the n points are sampled IID. Okay? And in fact, because I'm going to be thinking about reductions that might increase the sample complexity of various problems, it'll sometimes be convenient to think about the algorithm as having sampling access to D. When it wants to query a new person, it can just, sample a new person from D. And so when I say sample complexity, like what you should think about in this talk is how many times I have to sample a new person from this distribution. Okay, so a local randomizer is just an epsilon differentially private algorithm of a single data point. Okay, and we can talk about the set of all local randomizers. And a transcript, which is sort of the complete observable record of an interaction, I'm going to think of as just a vector of 4 tuples, where each 4 tuple records what happened at a single round. Okay, so the thing recorded in one of these 4 tuples is an index I of a user who was asked a question. Okay, a local randomizer RT, what question were they asked? A privacy parameter epsilon t. Okay, that's really a property of the local randomizer, but I'm going to talk about it a lot, so let's just, redundantly include it in the transcript. Okay, so RT is epsilon t private. And then there's YT, which is the answer the user gave. YT is a sample of the output of the local randomizer applied to the data of person IT. Okay? And the thing that will coordinate a local that will coordinate a computation in the local model is a protocol. And the way I'm thinking of a protocol is it's going to take as input a transcript, a record of what has happened so far, and it's going to decide what happens next. Okay, so given a record of what's happened so far, it will either decide that the protocol is over, okay, or it will decide what to do next, which corresponds to choosing the next person it's going to ask a question to, what question it's going to ask them, and what privacy parameter that question will have. Okay. So here's, like some pseudocode just making clear what happens when you have a protocol and you run it. Okay, so we've got our n users, and now for some number of rounds that if I don't specify the mechanism is sequentially interactive, could be arbitrarily large. The number of rounds could be much bigger than n. We'll, for each round, we will let the protocol look at the transcript of what's happened so far. Okay. It might decide we're done, in which case we just output the transcript. Or it might decide we're not done, in which case it tells us, okay, I'd like to ask person IT a question. I'd like to have them run local randomizer RT. It'll have privacy parameter epsilon t for this talk, ignore delta. And then we'll have user IT run the local randomizer on their data point. That gives us yt, and that's the next entry in the transcript, and we continue. Okay? So when I say that I think that when I define what it means for a protocol to be epsilon differentially private in the local model, what I mean is that this algorithm, when instantiated with A, should be differentially private. Okay, that the thing that this algorithm outputs is the transcript. Okay, and so this running of the protocol, which maps data sets to transcripts, that should be differentially private. Okay, that's what I mean. Katrina.
Am I reading this right, that one of the individuals you interact with is not allowed to carry state?
They don't need to. So the way I'm thinking about things is the protocol is just telling, the protocol carries all of the state that's necessary. But you could allow the individuals to carry state.
Okay.
I guess your definition still seems to allow some kind of pathological behavior. For example, your protocol could say, ask the same person twice for infinite differential private version of their answer, and if those two don't agree, then you can violate privacy completely, and that would still be private under this definition. So don't you want to kind of allow the users to behave arbitrarily rather than, all users other than me should be allowed to behave arbitrarily?
Are you asking sort of like about a difference between like an honest but curious model and an adversarial? I'm not sure I understand
Yeah,
that.
I guess since...
So, but the RT has an epsilon t equal to infinity in your example?
For one user, but then that may allow violating privacy for another user.
So in general, I'm gonna
You're talking about a single epsilon.
yeah, like we require that like with probability, this algorithm has to be differentially private, epsilon differentially private in all of the users. So it sounds like what you're describing wouldn't be.
Oh, actually, no. So here, the fact that I get privacy can depend on the fact that you are honestly executing your protocol. Because your randomness is kind of inbuilt in here, right? While we would really want it to be the case that even if you are completely dishonest,
Yeah.
I get privacy.
You're worried about people not running the randomizers.
Right.
Yeah, I don't think, I think you could, well, we'll see as I go on. I don't think anything I'm going to say would break under that model, but let's stick with this definition here.
Errol,
Yes.
is it essential for your model that the data is drawn IID, or?
You could generalize it a bit, but a lot of the things I'm going to talk about are about sample complexity, and you need to specify somehow like what it means to get like more samples. So that this is the sort of most straightforward way to talk about that.
Right, but you still would want like a for all x quantifier in the...
For the privacy.
Like the follow experiment doesn't take the data as an input.
Pretend it takes the data as the input for now. So yeah, the privacy should be for all pairs of neighboring data sets.
One more question.
Okay.
So here, kind of technically in this definition, my privacy depends on the fact that all the other people not only follow their protocol but don't observe the output of their randomizer.
What do you mean don't observe the output of the randomizer? That's part of the transcript.
Oh, I see. Sorry.
Okay. Okay. So in this model, we can think about three kinds of interactivity. Fully interactive means we essentially have no restriction on what this protocol looks like. The length of the protocol can be arbitrarily large. Sequential interactivity just means that for any user, there's at most one index in which they are the ones queried. Okay? So in particular, the number of rounds is at most n. And a non-interactive mechanism is a special case of a sequentially interactive one. Everyone sends at most one message. But now the local randomizers can all be chosen in parallel. Okay, the choice of personalized local randomizer doesn't depend on the outcome of the other users.
Go back for a second.
Yeah.
So between fully interactive and sequentially interactive, what's the nasty thing that happens in the first one?
So in a fully interactive mechanism, I could ask you a question, I could ask Kunal a question, then I could come back to you, I could keep doing this. The protocol could run for a really long time.
But there is something a little bit in between the two, right?
You could imagine defining things in between.
Like we could kind of have going rounds of every round of the protocol, like everybody is exactly, my local randomizer is always epsilon dp for that particular round.
Yes, and we'll talk about the connection to your definition of local differential privacy in a minute.
Or whatever I was using. Yeah.
Yes. Okay. So we've seen in a bunch of talks that there's a lot of advantages to non-interactivity. In particular, often communication is a bottleneck, and since non-interactive mechanisms can be fully parallelized, that's great. Sequential interactivity loses that, but it has its own advantages. In particular, it's much more powerful. So we've seen in both Vitali's talk on Thursday and Abradeep's talk from today and other good work that there can be exponential gaps between the sample complexity for solving natural learning problems when you go from non-interactivity to sequential interactivity. Okay. And there's other advantages. The protocols are still relatively short, only n messages, and you don't have to go back and locate specific prior users. So if I get on an airplane and turn my phone on airplane mode, it doesn't like break the protocol. And so one thing I want to think about is, what are the advantages of full interactivity? Right, there's a bunch of disadvantages, but like perhaps we get even more power. Okay, so we can think about is the fully interactive model more powerful? So not a lot is known about this. So many of the sort of powerful lower bound techniques, including those developed in sort of the seminal work of Ducci, Jordan, and Wainwright, for proving lower bounds in the local model for interactive protocols, they hold only for sequentially interactive protocols. Okay, and we saw a talk by John on Tuesday. Well, I watched it on video. I wasn't here, but many of you saw it, in which, in work together with Ryan Rogers, they were able to extend some of these lower bounds to a subclass of fully interactive mechanisms in the way I'm defining them. Okay. To show that there are certain non-interactive mechanisms that are optimal within this restricted subclass. Okay? And it wasn't known, as far as I know, whether you get additional power by moving to full interactivity.
So one more thing. Also, one of the points was that epsilon can be bigger than 1 for our results.
Yes, we'll see how epsilon comes in here.
Yeah, no, that's all.
Yeah, there's other nice things about that paper that you... but this is what's relevant here. Okay, so let me tell you about what we do, and then we'll see how much of it we can get through. Okay. So first, we just sort of find some parameter that turns out to be useful for categorizing fully interactive mechanisms that we call their compositionality. Okay, I'll tell you what that is on the next slide. But this is sort of an extremely relevant parameter, and roughly the definition that John and Ryan use is what we would call the set of 1 compositional mechanisms. Okay, so here's our upper bound. We show that if you have any k compositional mechanism, potentially fully interactive, we can generically compile that into a sequentially interactive mechanism that exactly preserves the transcript distribution, okay, so solves whatever problem you were solving just as well, such that the blow-up in sample complexity is only on the order of k, or e to the epsilon times k, so bigger if epsilon is big. And that means that if you have a 1 compositional mechanism, then there's nothing you can do with a fully interactive protocol that you can't do with a sequentially interactive protocol. The next result is that our dependence on this parameter is tight. Like, this is actually an important parameter. Okay? And this is also, I think, the first separation between fully interactive mechanisms and sequentially interactive ones. So in particular, for every k, we identify a family of problems that can be solved by a k compositional mechanism with some sample complexity n, which depends on k, such that if you wanted to solve this problem with a sequentially interactive protocol, you would need a factor of k more samples. Okay? So you could imagine reductions that have different dependencies on other parameters, but you can't generically give a reduction that has a better dependence on this parameter, which I'll tell you what it is in a moment. And then finally, we have some stuff to say about hypothesis testing as well. So in particular, for any simple hypothesis testing problem, or more generally, for any compound hypothesis testing problem where both the null and the alternative are convex, closed under mixtures, then you don't need interactivity at all. The optimal test, even amongst the set of arbitrary interactive mechanisms, is in fact non-interactive. Okay. So let me tell you what this compositionality means, because that's sort of the crucial parameter that underlies our work here. Okay. So let's say that an epsilon private protocol is k compositional if, when I look at, for any single user, the epsilon parameters of the local randomizers that I ask them to run. Okay, so the epsilon parameters corresponding to a single user. Okay, they add up to at most k times the overall privacy guarantee of the mechanism. Okay, and if k is 1, let's just say that A is compositional. In fact, we only really need that this holds on average. So in fact, if I just sum up all of the privacy parameters used over the course of the mechanism, it should sum up to at most k times n times epsilon. Okay. So one compositionality is a pretty natural subclass. If you've analyzed your mechanism with the composition theorem for differential privacy, just by adding up the epsilons, then you get a one compositional mechanism. Okay, and it's related to the class of mechanisms that John and Ryan prove lower bounds for. Roughly speaking, they're proving lower bounds against what we would call one compositional KL stable mechanisms. Okay, so on the one hand, we're going to sort of generalize this to allow K to be bigger. On the other hand, we really do require differential privacy. KL stability is not enough for us. Oh. So it's natural, like compositionality is so natural that you might conjecture the first time you're thinking about this that like everything is compositional, right? Like, the privacy parameters add up. So it's like helpful to see a simple example demonstrating that that's not the case. Like there are mechanisms that are not k compositional for arbitrarily large k. Okay, maybe here's the simplest example, which is related to the analysis in rapport. Okay, so let's suppose that the data universe consists of the d standard basis vectors in some d-dimensional space. So your data point has a 1 in some position and a 0 everywhere else. Okay? And remember what randomized response is. If I run randomized response on a bit, then you will output that bit with probability e to the epsilon over 1 plus e to the epsilon. Otherwise, you'll flip the bit. Okay. So now, just what I'm going to do is for every person and for every coordinate, I'm going to ask them to run randomized response on, for person I, run randomized response on coordinate j of their bit with privacy parameter epsilon. Okay? So every person is running d local randomizers, each of which really is epsilon differentially private and is not epsilon prime differentially private for any smaller epsilon, because there really is, like a neighboring data set that changes the probability of the bit that you're going to output by, an e to the epsilon factor. And yet, because of a histogram structure, essentially, that if you change to a neighboring point, you only change 2 coordinates of the vector, this protocol isn't d epsilon private, it's 2 epsilon private. Okay? So this protocol fails to be k compositional for any k less than d over 2. And we can take d to be as large as we want. So it's not that one compositional mechanisms are all there is. Okay, one compositionality is what you get if you only analyze your algorithm using the composition theorem, but there are algorithms that have non-compositional analyses. So let me try to tell you how the upper bound works, how we get from full to sequential adaptivity with a blow up in sample complexity that's bounded by k. And it's based on sort of 3 ideas. So the first one is really, not an algorithmic idea, just sort of a thought experiment. Okay, we're gonna look at our protocol. We're gonna imagine that it's actually a slightly different pretend protocol, but it's going to induce exactly the same transcript distribution. So for the rest of the argument, we can try to simulate the transcript distribution of this pretend protocol. Then we're going to sort of simulate the distribution of this pretend protocol with a sequentially adaptive protocol, basically using rejection sampling and Bayes rule. Okay, I'm going to go through all of these in more detail. This step will get us to sequential adaptivity, but it might really blow up the sample complexity. Okay? And so the third step is to slightly generalize this very nice idea of a data-independent decomposition of local randomizers that Borja told us about on Wednesday, which allows us to shrink the sample complexity back down. Okay, so the sample complexity of the mechanism that we get here is going to blow up from from n to roughly t, the number of rounds the protocol ran, which could be really big. But the third step is going to get it back down to e to the epsilon times n times k. Okay, so that's the high-level overview. Oh, so let's go through these one at a time. So here's sort of the pretend mechanism. It's almost exactly the same as the regular mechanism with one change. Okay, so this is sort of a Bayesian thought experiment. So what's really going on, of course, when we run a locally private protocol is we sample the data, then the data's fixed. Once we start running the mechanism, I'm gonna, be asking people questions. When I go back to ask Adam another question, it will, it'll be the same Adam that I asked the first question to. Okay? But why don't I imagine that that's not what happens when I go back to ask Adam a question for the second time? I actually resample his data afresh, not from the prior distribution, not from the real data distribution, but on the posterior distribution conditioned on the transcript I've seen so far. Okay? Okay, I don't know what this posterior is. It might be hard to think about, resampling Adam, but, it's something I can imagine, and it just sort of by Bayes' rule, or maybe even just the laws of conditional probability, it's not too hard to see that no outside observer can tell if I was doing this resampling or not. It doesn't change the output distribution on transcripts, right? In general, if I have any pair of sort of jointly distributed random variables, I can sample x and I can sample y conditional on x, or I can sample x, I can sample y conditional on x, and then I can resample x conditional on y, and I get the same joint distribution. That's all we're doing here. Okay, so our target can be to simulate the transcript distribution on this thing. Okay, right now every time before I ask someone a question, I resample their point from the posterior. Okay, now I don't know how to sample from the posterior, okay, but I do know how to sample from the prior, right? I can ask a new person, I can sample a new person from the distribution, and I can ask them a question, right? That's the kind of thing I can do with sequential interactivity. So the idea will be to try to do rejection sampling. I've got a sampling distribution, this sort of data distribution. The thing I'm trying to simulate is also sampling a new person every time it asks a question, but it's sampling from the posterior distribution on the transcript. Okay? So, the idea that we want to implement is whenever it's time to ask Adam another question, I'm going to sample a new person. Okay? Then I will ask them to employ rejection sampling, and if they succeed, then it will be a sample from the posterior, and I'll continue. Okay? So for rejection sampling, what I would want to do, right, if I want to sample someone from the data distribution conditioned on the transcript, but I can only sample from the data distribution, is I would want to accept with probability proportional to the ratio of the density of the probability of x given the transcript divided by the probability of x. Now there's a problem, which is that, well, I as the protocol, but more importantly the individuals running the local randomizers, don't know what these quantities are in either the numerator or the denominator, because we don't know what the prior distribution is, and so we don't know what the posterior distribution is. But we're sampling, right, like it's nice that like the thing in the numerator is a posterior and the thing in the denominator is a prior. Because that means I can apply Bayes' rule and get an equivalent expression. And now the thing in the numerator is something that the user can calculate given just their own data and the transcript so far. What's the probability that they would have generated the responses recorded in the transcript and attributed to them given their own data point? Okay. The thing in the denominator, okay, we still, the probability of the transcript, we still don't know how to calculate that thing because we don't know the data distribution, but it's data independent. Okay? And so, right, we only need to sample with probability proportional to this. So I can rescale this by any data independent quantity. And so it suffices to have people accept with probability, the probability that their part of the transcript would have been generated given their data point, divided by twice the maximum probability over any data point they could have had that their part of the transcript would have been generated with that data point. That's something that, those are quantities that they can compute with only the information they have on hand. Okay. So this is nice. We can do the rejection sampling. The users can do the rejection sampling with only information they have on hand, the transcript and their own data point. It's epsilon differentially private to perform this sampling because the fact that the transcript was epsilon differentially private allows us to bound the ratio of the prior to the posterior.
What's the 2 doing?
So this number is going to be, the 2 is making it sort of, the 2 is important for differential privacy. So this number is going to be something that's bounded, that's, you know, between 1 and e to the minus epsilon. It would be bad if it were 1. Okay. And it usually succeeds, or it succeeds with constant probability if epsilon is a constant, right? It's the sort of success probability is 1 over 2 times e to the epsilon. Okay. So whenever our original protocol wants to ask someone a question, okay, like wants to run a local randomizer on, you know, run another local randomizer on Atom, okay, we use this rejection sampling routine. Okay, we're going to now, until someone passes the test, keep sampling a new person from the distribution, ask them to compute this probability, which they can do from their own data, ask them to sample from a Bernoulli distribution with this probability, which is epsilon differentially private. And if they pass, then we ask them the local randomizer to employ the local randomizer we wanted to run. Otherwise, we sample a new person. Okay. But it won't. It'll pass with constant probability. Okay. So where have we gotten so far with this idea? The upshot is that we can exactly simulate the transcript distribution of a fully interactive protocol now with a sequentially interactive protocol. But our sample complexity might really have been blown up. Oh, but before we get there, our privacy cost was potentially blown up by only a little bit, right? It's blown up because now when someone successfully passes the rejection sampling step, I've asked them to answer 2 differentially private queries, basically. The rejection sampling cost them potentially epsilon, and then I ran an epsilon t local randomizer. Epsilon t is going to be less than epsilon, so by composition in the direction in which it works, this is only 2 epsilon private. Okay. The big problem is that the sample complexity has been blown up, because now I'm running, there's t rounds to this protocol. T could be very big, and I'm asking each local randomizer to a new person, whereas the fully interactive protocol was asking each person on average t over n questions. Okay, so I don't know. Right, so I've blown up the sample complexity from n to 2 times e to the epsilon times t, right? Because now I'm asking everyone sort of t questions, and it potentially takes me, in expectation, 2 times e to the epsilon people before I find one good enough to answer a question. Okay? And this is bad because I don't know a priori how big t is. It could be arbitrarily large. So we need one more idea. Okay, and this is where we're using the idea of the data independent decomposition from Borja et al. Okay, so we actually need a slight generalization of their theorem, but let me first remind you of their theorem. Okay? So what they show, for a very different purpose, is that if you've got an epsilon private local randomizer, you can in fact write it as a mixture distribution where there's two mixture components. Okay? Omega is a data independent distribution. Okay? And then this other component, dx, this does depend on the data. But the weight on dx is small. Okay, so almost all of the weight of e to the minus epsilon, which when epsilon is small you should think of as 1 minus epsilon, is on the data independent part. Okay, so that's nice, and it sort of is at least suggestive of a way that you could sort of reduce sample complexity, because only with some small probability do I actually need to look at someone's data in order to answer a question that I have to ask of them. The problem is that if you, oftentimes this data dependent part of the distribution is just like a point mass on their private data. It's just, tell me your private data. And so for the protocol to, for the local randomizer to be private, although it has this decomposition, it's really crucial for the privacy that it not become public which of the realized mixture components I sampled from, right? That's really crucial because this distribution could just be announcing your data in the clear. Okay? So we need this generalization, which isn't, once you see what they do, it's not too hard to come up with this generalization. Okay, here's what we can say. Suppose you've got an epsilon prime private randomizer R. And now, why don't you pick some epsilon which is bigger than epsilon prime? Okay? I can decompose your randomizer R into, again, a mixture of two distributions. Okay? One of them is going to be data independent. The other of them will be another local randomizer, okay, where the this local randomizer will have a privacy guarantee. This local randomizer will be epsilon private, which is less private than the original randomizer, which was epsilon prime private. But the weight that I put on the epsilon private local randomizer, looks like this, which is easier to interpret when epsilon and epsilon prime are, kind of small, less than 1. It's roughly epsilon prime over epsilon. Okay, so by making epsilon bigger, I can reduce the probability that I need to actually talk to a person in order to answer their question, in order to have them answer a question, but increase their privacy costs in the event that I need to talk to them. Okay? And now, now I can get privacy, worse privacy, epsilon instead of epsilon prime, but I can get some privacy guarantee even if I reveal publicly which mixture component I'm sampling from. Okay? And you can trade off the privacy cost with the probability of needing data. Okay. So now here's the idea. Okay? Right? Remember, we've already gone from a fully interactive mechanism to a sequentially interactive mechanism. Okay, but the sample complexity is really blown up. But now, okay, we're going to run that sequentially interactive mechanism, and every time the protocol tells us to run an epsilon t private local randomizer, we're going to publicly flip a coin. Okay? And with roughly probability 1 minus epsilon t over epsilon, it's going to tell us we can sample from this distribution by sampling from the data independent distribution. We don't need to actually sample another atom. Okay, in which case we won't sample another atom. We'll be able to get yt, which we need to continue the protocol, without expending another sample. Okay? With the remaining probability, epsilon t over epsilon, we actually do need another person, in which case we will use this slightly less private randomizer, R tilde, through our rejection sampling routine. Okay? And again, when the epsilons are small, I'll show you that we have, all of this stuff generalizes to when the epsilons are big, but the bounds are more messy. When the epsilon is small, the probability that I need to sample a new person is roughly epsilon t over epsilon. And so if you look at the expected number of users that I need to actually sample, right? It's the sum over all of the rounds of the privacy parameter of the local randomizer at that round divided by epsilon. And if the mechanism was k compositional, that's k times n. Okay, right? Because k compositional means the sum of the epsilon t's is at most epsilon kn.
like if we were to apply this to the example you gave earlier of this sort of histogram. So what this is there's an equivalent protocol where in all but one round I just make up the answer myself, and then just like one round I talk to the user, but in that round ask for like a much more accurate answer.
That's right.
And sort of distribution this will generate the same thing.
Yeah.
It's a constant cost in epsilon.
Right, this is like some generic way to like trade off, like if you have an existing protocol, I can like trade off privacy with sample complexity. Okay, so you put it all together and it looks
This
like
also
that.
shows that K-compositionality is quite common. Okay.
What do you mean?
Because in general, like in many of the rounds that I participate, I'm actually sending data independent answer.
If you are, yeah, if your mechanism is compositional, then you might as well be almost always sending data independent. So you can put it all together and it looks like that, but it's really just these three ideas, each of which is pretty simple. Here's the theorem in the end. Okay, for any fully interactive epsilon private K compositional protocol, there's a sequentially interactive protocol A prime that is 3 epsilon private. Produces exactly the same transcript distribution as the original protocol, and with high probability has up to low order terms sample complexity that's like the original sample complexity, larger by a factor of k and e to the epsilon. Okay, so in particular, for compositional mechanisms, if k is 1, then, and up to this factor of e to the epsilon, any lower bound you prove for sequentially interactive mechanisms also holds for compositional fully interactive mechanisms. And this is tight. I only have 8 minutes, but let me try to show you the problem that is sort of hard for sequentially interactive mechanisms, but is easy for K compositional fully interactive mechanisms. Okay, and it's a sort of variant of a pointer jumping problem. So imagine a tree. Okay, there are levels of this tree. I know it looks like D is 4, but trust me, it's D. D levels. And imagine that at each level, the vertices are labeled with a bit called left or right. Okay? And let me name for, at a particular level I will call Zi just the vector of the labels of the vertices at that level. Okay? So once I've labeled the tree like this, it induces like a unique root to leaf path down the tree. Okay? So call something like this when I assign, these labels to every vertex in a complete binary tree, an instance of the multi-party pointer jumping problem. Okay. Now, I want to turn this into a problem that we can ask a locally private protocol to solve. So let me define a distribution from which people are going to be drawn. Okay? Okay, so given an instance Z is the labelings. Okay, I'm going to define the following distribution. First, select a level of the tree uniformly at random. Okay, and then output the data point that is the pair equaling the level of the tree and the labels for that level of the tree. Okay, so people, when you sample a new person from this distribution, they have a level at random and they get all of the information about that level of the tree. Okay, all of the people at the same level have the same information. Okay, but it's private what level you are. And the problem, right, the problem we want to solve is given n samples from this distribution, find the path. Okay. Okay, so we have a separation. So the first claim is that there's a decompositional, fully interactive mechanism that can solve any instance of this problem with sample complexity that's in the order of d squared over epsilon squared. Okay, here's how it works. Here's the first question I'm going to ask. It says, if you are at level 1, then use randomized response to tell me your child. Okay. If you are not at level 1, just flip a coin and tell me a random bit. Okay, because remember, I don't know who's at level 1 and who's not. That's part of the private data. So this is the description of a complete local randomizer. If you're at level 1, you run randomized response. If you're not at level 1, you just flip a coin. Okay. We try to identify from that, and we're going to rig things up so that we can, with high probability, what is the sort of correct child. Okay. Then I'm going to call the child P2. Okay. Then I'm going to run another local randomizer. Again, I ask, in each of these rounds, I ask everyone to run this local randomizer. So it's fully interactive. People are answering many questions. Okay.
So if my level is R, I learn that entire layer, right? Not just one. Okay.
If your level is R, you learn like.
My private data is that entire.
It's the whole layer, exactly. Okay. So in the second round, hopefully I've learned sort of the first edge down this tree, and so now I ask, okay, if you happen to be at the second level, then tell me who your child is with randomized response. If you're not at the second level, again, I don't know who is and who's not, flip a coin. Okay. More generally, I'm going to continue in this way, and assuming we've succeeded up until now, I'm going to ask you at the Lth round, if you're at the Lth level, report the child of PL with randomized response. If you're otherwise, flip a coin. Okay. So how do you think about analyzing this protocol? Well, first you need to argue that you have enough signal to correctly, with high probability, identify the child. That we're going to correctly build up this path one at a time. Okay. So, if n is something like d squared over epsilon squared, how many people are at each level? Well, the probability that you're at a particular level is 1 over d. Okay, so there's roughly n over d people at each level. And that works out, if you've picked this to be n, to be root n over epsilon people at each level. And root n over epsilon is just at the threshold of, the kind of signal you can distinguish from the noise that's introduced by randomized response when you have n people. Okay, I can estimate a sum when I've got n people up to error roughly root n over epsilon. Okay, so we've rigged things up so that that's exactly the level of signal we have, and so we can correctly identify the child at each step. Okay. How about the privacy analysis? Well, each user is running an epsilon private local randomizer d times, one for every level of this tree. But embedded in here, you will recognize, is the histogram structure of the example I gave at the beginning of the talk, right? Because every person is only at a single level, and so we'll only have to answer in a data-dependent way once, even though I've asked d questions. In particular, any sequence of responses, any sequence of bits, has probability that's bounded between 1 over 2 to the d minus 1 times 1 over e to the epsilon plus 1 and 1 over 2 to the d minus 1 times e to the epsilon over e to the epsilon plus 1. So even though the epsilon t, your epsilon t's add up to d times epsilon, the whole protocol is actually epsilon private. Okay, so it's k compositional, epsilon private, k compositional, where k is d. Okay, I just have 2 minutes left. Let me give you some intuition for the lower bound, which is that any sequentially interactive protocol actually requires a factor of k more samples. Here k is d, right? It was a d, k was d in our upper bound construction. And so that's going to turn into a lower bound that says you need d cubed over epsilon squared samples if you're sequentially interactive. Okay. The actual proof is a long, delicate induction, but I think the intuition is pretty straightforward, which is that even to identify a single edge, even at the top level, you really need d squared over epsilon squared examples. And that's because you really can't estimate a sum in the local model to error when you've got n people to error better than root n over epsilon. Okay. So you sort of need root n over epsilon people at the relevant level, but when I sample a person, the chance that they're at the relevant level is only 1 over d. So to guarantee that you're going to have that, you sort of need n over root n over epsilon people. Okay, which means that you sort of need d squared over epsilon squared examples to answer this question at each step. But if you're sequentially interactive, you can't reuse people. After I've used everyone to answer the first question, I need like a new sample to answer the second question, and a new sample to answer the third question. Okay, that's not a proof, but that's maybe the intuition for why this problem is hard for sequential interactive mechanisms. Okay, let me just tell you, since I'm out of time, our theorems for hypothesis testing, but not tell you anything about it. Optimal locally private hypothesis tests for simple hypothesis testing are non-interactive. Okay, so you get optimality even with respect to the entire class of fully interactive mechanisms. You can generalize that a little bit to compound hypothesis testing, where both the null and the alternative are closed under mixtures, or convex. Okay, and you can ask me that there's a proof that's not in the paper because we ended up proving something stronger, but in maybe like a less interesting way. So you can ask me offline, if you want to get this result just for compositional mechanisms, then you can have sort of a neat little reduction using amplification by shuffling, which I, unless someone asks me, I won't go through. So thank you.
Question?
So in particular, what that says is the kind of body of work that's been built up on lower bounds for non-interactive and sequentially interactive mechanisms so for those simple testing problems where there are tight upper and lower bounds, then those bounds are also tight for the kind of full.
That's right.
Fully interactive.
And more generally, yeah, any lower bound you've previously proven for sequentially interactive mechanisms also holds for one compositional mechanisms, and more generally holds for k compositional mechanisms up to some loss that's like a factor of potentially k in the sample complexity.
No, but the requirement in the alternative is convex is stronger.
Yeah. So definitely
Usually it's not.
the most interesting special case.
The simple testing.
Yeah, the most interesting special case of this is the simple testing problem.
So I was wondering, can you create also a more than polynomial separation between those two?
Yeah, great question. So I think that's the main open question coming out of our work. So what we showed, right, is that there's this parameter k that is sort of crucial, right? If you have a k compositional mechanism, you can get a sequentially interactive mechanism with a blow-up that's a factor of k, and you can't do better than that in terms of k. Now our lower bound instance, which shows that this dependence on k is tight, never results in a blow-up that's more than a factor of square root of n. So you might conjecture, and I do conjecture, that you can simulate any fully interactive mechanism with a sequentially interactive mechanism that uses only n to the 3/2 samples. You can't do better than that because our lower bound also shows an n to the 3/2 bound in terms of n, but I kind of, due to some not very well-grounded intuitions, believe that's the right answer.
Can you do something similar through the simulation in the SQ model?
Something similar to what?
Like the simulation in the SQ model also would give you translation from any protocol into the SQ model, and then you can simulate back. So in a sense, you can begin with what any interactive local model protocol, and through this get back into a protocol that is where you're not going back to.
So I don't. Adam probably knows a better answer to this question.
Yes, so certainly as written in our paper, I don't think you'd get anything like we had some blow-ups in terms of round complexity and things like that that I think would end up kind of boiling down to assuming compositionality or something like that. I'm not quite sure, but not assuming compositionality, but like
we're having
we were missing certainly missing that really that crucial idea that
definitely.
you can.
But it does. This decomposition does seem like a somewhat generic way to reduce sample complexity if you are not making really tight use of your privacy budget.
What about tasks where the inputs are given that not drawn from the distribution?
Yeah, so so it's not clear how you would even, or it wasn't clear to us at least, how you would even pose that question, because the form of the results we find is that there are some problems that need like more data to solve. So the question is, if there's not a distribution from which the data is drawn, what does it mean to like solve the problem with like larger sample complexity?
No, the question is if you have a protocol that queries some person many times, is that essential? Is it essential to query one user more than once?
So basically it's not if the mechanism is compositional. Like if, I think a lot of this would generalize, at least in the case where you don't really need to blow up the sample complexity, so the one compositional case, to symmetric mechanisms that are sort of permutation invariant. Like it is sort of important that like a priori all of the people be sort of the same, because the whole thing that we're trying to do is to avoid asking the same person multiple questions and to instead like ask those questions to different people. So it does seem like you need some kind of symmetry at least. But I think a lot of this would go through for permutation invariant mechanisms, at least like for the one when you start needing to blow up the sample complexity, like for K compositional mechanisms, it's not clear what that means if you don't have a source from which to gather more data.
Is it clear that the same separation would hold if we look at epsilon delta?
That's a good question. So it's related to the question that I guess you talked about at the open problems session, which is when is it that we can sort of reduce epsilon delta privacy to epsilon privacy? And maybe you know more about this than me. It seems like the only thing the existing proof is using about like sequential interactivity is like that there's only n randomizers.
Right.
And so like at least for fully interactive protocols for which t was polynomial in n, it seems like you could do the same thing and you'd need delta to be smaller than something in t. Right, so it seems like that would be almost immediate, that if for protocols for which the round complexity was polynomial in n, all of this should go through up to some log t factors, also for epsilon delta. But I don't know if there's like something more subtle that goes wrong with that reduction. We didn't work it out.
All right, thank you. Since in the rejection sampling step, since you're conditioning on the transcript, this may get back around my question. There's an assumption that the randomizer can't be hidden from you. You need to be able to account for that in your conditioning. Am I understanding that right?
Yeah, but even to run the randomizer on the data, you need to know what it is, right? Like, what is it? What do you mean?
Well, I guess the randomizer is running on some local environment.
So the rejection sampling is also happening in the local environment.
Oh, I see. Okay, sorry.
Yeah. So to do the rejection sampling, right, you need to know what the data point is. Only the user knows that, not the protocol.
And then that full transcript is available. You have the full transcript available locally.
You have everyone can observe the transcript.
Okay. And so then you have. I think I understand. I think so. You see the other, but you see other randomizers as well.
You see the output of the other randomizers.
I mean, the protocol, like you're designing the protocol, so you could just hand that information to the next guy, right?
Yeah. But like, the whole point is that in the end, like the thing that should be differentially private is the whole transcript. So like everyone can see the transcript.
Oh, let's take it offline. Thank you, Peter.